Hello everyone, I'm Salih Mert Uzun, a second-year computer engineering student at Bilkent University. This is my PHYS102 project on the experimental verification of Faraday's law of induction. The goal of this experiment was to isolate and individually measure how three different parameters affect the peak-induced EMF generated in the coil, those being the velocity of the magnet, the number of turns in the coil, and the distance between the magnet and the coil. For the setup, I mounted a magnet on a pendulum and swung it through the center of a stationary coil connected to a multimeter in DC millivolt mode. A slow motion camera was used to accurately capture the peak voltage readings. For the first part, I varied the release height of the pendulum while keeping everything else fixed. Since a greater height means greater speed at the bottom, and speed directly drives the rate of flux change, EMF is theoretically expected to scale with the square root of the height. In the second part, I kept the height and distance fixed and tested coil with different numbers of turns. According to Faraday's law, EMF is directly proportional to N, so I expected a clean linear relationship here. In the third part, I fixed the height and turn count and varied the distance between the magnet's lowest point and the coil. Since the magnetic field of a dipole drops with the inverse cube of distance, I expected a sharp non-linear decrease in EMF. Here I am demonstrating one of the measurements on effect of magnet's velocity on peak-induced EMF. And here you can see one of the examples of how I measured the effect of winding density on peak-induced EMF. And finally, here you can see an example of how I measured the effect of distance between the coil and the lowest point of the magnet on the peak-induced EMF. Here you can see my experimental values along with their theoretical counterparts of velocity's effect on peak-induced EMF. And here you can see my experimental results and theoretical expectations on peak-induced EMF based on winding density. And finally, here you can see my experimental results of measured peak EMF based on distance between coil and lowest point of the magnet. My results confirmed all three of these theoretical predictions. The average error across measurements was around 13%, which is likely due to error resistance, minor misalignments, and the limited precision of the multimeter. What this experiment taught is that electromagnetic induction isn't just an equation, it's a precise measurable physical phenomenon that responds predictably to each variable. Understanding these dependencies is fundamental to how real-world devices like generators, transformers, and wireless chargers actually work. Thank you for listening.